afternoons? Huh? Who said no? Right?
No.
Who was it? Who said you don't like Friday afternoons? Why?
I just want to see the weekend already.
You what?
I just want it to be the weekend already.
Oh, already.
That's true.
See, I kind of view like Fridays as Christmas Eve. You know, you just, you know, you don't want it to be Christmas Eve already, but you're anticipating. All right. So yesterday in our study of the chain rule, right? We came up with some formulas applying the chain rule. Okay. The first one we came up with was the general power rule. The derivative with respect to x of g of x to the nth power is equal to n times g of x to the n minus 1 power times g prime of x. And all these formulas we come up with will end with g prime of x, right? The derivative of the inner function. Okay. Then next we came up with the derivative of respect to x of e raised to the g of x power. Right? So the exponent on the number e is not just x, right? It's e to the g of x. And that derivative, right, is equal to e raised to the g of x times g prime of x. Right? So whenever we differentiate the natural exponential function, it's always itself, okay? And then times the derivative of the numerator, or the exponent, excuse me. And then we came up with the derivative of any exponential function, a to the x, and that's equal to a to the x times the natural log of a. And then applying the chain rule to any exponential function, we have the derivative with respect to x of a to the g of x power, and that's equal to a raised to the g of x power times the natural log of a times the derivative of the exponent, g prime of x. Okay. So let's do a couple examples involving the derivative of any exponential function. So if f of x is equal to 2 to the x power, then the derivative of f of x, f prime of x, is equal to 2 to the x times the natural log of 2. If h of x is equal to 3 raised to the x squared minus x power, then we have to apply the chain rule. H prime of x, right? So the derivative of this exponential function is itself times the natural log of the base, which is 3, right? And then times the derivative of the exponent. And the derivative of x squared minus x is 2x minus 1. Any questions on that? Okay. All right, so let's apply the chain rule to the trig functions. Now I'm not going to derive the chain rule for each 6 trig functions. We're going to do it for one, and then once you see the pattern, we'll extend it to the other 5. Okay. So And you notice that when I differentiated this guy over here, I did not say, okay, this is f of x, this is g of x, right? This is, we're doing that all up here, right? We know what f of x and g of x, f prime, g prime up here is, right? It's the pattern that's important, okay? All right, so the chain rule applied to the trig functions. So let's do it for sine x. So you know from 3.3 that the derivative of the sine of x, okay? So I'm going to go off on the side here, just to remind you of something. So you know when we write this, we read this as f of x, right? F is the name of the function, x is the input. Sine, cosine, right? So we have f of x, g of x, h of x, and so forth, okay? The sine, cosine, tangent functions, and so forth, they're just the names of special functions like these guys are. So this is the function sine of x, okay, with the x inside the parentheses here. And so instead of naming the function f, we name it sine. Okay. This is the function cosine of x, right? Cosine's the name of the function, just like g is the name of the function, but x is the input. Okay. Now, with trig functions, what goes into the trig function as input, we often call the argument. Okay. And that argument can be a function of x, okay, or it can be just a real number. Now, because sine, cosine, and tangent, right, the 6 trig functions are special functions, sometimes we drop the parentheses. So instead of writing sine of x like this, we just write sine of x like that. We give ourselves permission to drop the parentheses. Now we would never do that with f, g, and h. We always keep the parentheses. But with the trig functions, we often drop the parentheses. So this down here still means sine of x, just like this means f of x. Okay? So we can write cosine of x this way. You can write tangent of x this way. Okay? All right. So going back up here, the derivative with respect to x of sine of x is equal to cosine of x, right? I drop the parentheses. Sometimes I'll put the argument in parentheses and sometimes I won't, right? Doesn't matter. Means the same thing. All right, so now let's apply the chain rule to the sine function. So we're going to find h prime of x if h of x is equal to not sine of x, but the sine of g of x. So now I'm using the parentheses, okay? What's going into the sine function is g of x, not x, okay? And in this case, this is also the inner function, but it's also called the argument, because that's what's going into the sine function, okay? All right, so if we decompose h of x, you will see that the outer function f of x is sine x, the sine of x, then g of x is the inner function. Then with f of x and g of x, h of x is a composite of f with g. f of g of x. And f of g of x, right? You put g of x in for x and f of x, and you get the sine of g of x. Okay? The derivative of f of x, f prime of x, is cosine of x. So h prime of x over here, we know by definition, is equal to f prime of g of x times g prime of x. Derivative composite function, right? This is our composite function. H of x is equal to f of g of x. Derivative of that composite is f prime of g of x times g prime of x. Well, g of x, so f prime of g of x, to find f prime of g of x, you put in, replace x with g of x, right? So we have the cosine of g of x times g prime of x. So that's what h prime of x is equal to. So that's what the derivative of sine of g of x is equal to. Okay. So the derivative with respect to x of the sine of g of x, right? Again, g of x is the argument going into the sine function. You take the derivative, sine function, the outer function, right? The derivative of sine is cosine. So you have the cosine of the argument, g of x, and then you multiply that by the derivative of g of x. The derivative with respect to x of tangent g of x, that's equal to the derivative of the outer function. What's the derivative of the outer function tangent? Secant squared. So this is equal to secant squared evaluated at g of x, right? G of x is the argument going into the secant function, and then you multiply that by g prime of x. The derivative with respect to x of the secant of g of x is equal to the derivative of the outer function secant. What's the derivative of secant? Secant tangent. So we have secant g of x times tangent g of x, and then times derivative of the inner function g prime of x. And the other six follow the same pattern, right? So the derivative cosine of g of x, we equal minus, right? Derivative cosine is minus sine. So we'll have minus sine g of x times g prime of x. Right? So you get the same pattern, okay? Any questions on that? So, as an example, if y is equal to the secant of 2x plus 1, right? So the argument going into the secant function is a function of x, okay? Then the derivative of y with respect to x is equal to derivative of secant, right? Is secant times tangent. So we have the secant of 2x plus 1 times the tangent of 2x plus 1 times the derivative of the inner function. The inner function is 2x plus 1, right? So derivative of 2x plus 1 with respect to x is just 2. All right, any questions on that? All right. Let's do an example explaining why it's called the chain rule. And you may have noticed that when applying the chain rule, right, when finding a derivative using the chain rule, we work from the outside to the inside. You'll see that with this example. Okay. So, I have three functions. F of x is equal to the square root of x. G of x is equal to the sine of x. And h of x is equal to e to the x. You know how to differentiate all three of those functions, right? You know the derivative of all three of those functions, okay? So if f of x, g of x, and h of x are each of those equals each of those three functions, and y, right? The variable y is equal to the composite of f with g with h. Right? Now, most of the time when you see composite functions, you're just taking the composite of two functions. But you can take the composite of 3 functions, 4 functions, 5 functions, 6 functions, 7 functions, 8 functions. Right? It doesn't stop at 2. So we're taking y is the composite of f with g with h as a function of x. This is equal to f of g of h of x. Okay? Definition of composite function. This is equal to f of g of h of x. Okay? See that h of x is in the middle and all the way on the inside, and we're taking g of that, and then we're taking f of that. Okay? All right. Then, so we have our if and statement. Then, now I'm substituting, right, for h of x. Right, so the first thing we do to figure out what y is equal to, we replace h of x with what it's equal to, right? So y is equal to f of g of h of x, where h of x is equal to e to the x. So e to the x, right, is the inner function to g. Now g of, now we got to calculate g of e to the x, right, where e to the x is the inner function to g, okay? So now we got to evaluate g of e to the x. Well, g of x is equal to sine x, so we just replace x with e to the x, right? And we have g of e to the x is equal to the sine of e to the x. So here I'm using parentheses, right? in the sine function, right? So the argument going into the sine function is e to the x. Okay? So sine of e to the x is now the inner function to the function f, right? F is the outer, sine of e to the x is the inner. So how do we evaluate f of sine of e to the x? We put sine of e to the x in for x on the right-hand side of f of x. So this is equal to the square root of the sine of e to the x. So remember, e to the x is the argument going into the sine function. This is right, this parentheses, right, it contains the argument e to the x. Okay. Well, we're going to differentiate this function. And you know, when you take the square root of something, that's the same as raising it to the 1/2 power. So we have the sine of e to the x raised to the 1/2 power. Okay? So far, so good? All right, so now we're going to differentiate. So we're going to find the derivative of y with respect to x. What rule involved in chain rule are we going to use first? The general power rule, right? This inside the brackets is a function of x, right? Call it r of x. We have a function of x raised to the 1/2 power. So we're going to use the general power rule. Right? That's what the general power rule says, right? You have a function of x raised to power n. You use the general power rule to find the derivative. So by the general power rule, we bring the exponent 1/2 down in front of the bracket. Subtract 1 from the exponent. 1/2 minus 1 is minus 1/2. And now we multiply this by the derivative of the inner function, right? So we got to multiply this by the derivative with respect to x the sine of e to the x. Okay? It's application of the general power rule. So now we got this here, 1/2 times this minus 1/2 power times this derivative. To find this derivative, we got to use the chain rule applied to the sine function, right? E to the x is the inner function. Sine is the outer function. And we just had it up here on the board earlier. Okay. So the derivative of y with respect to x is equal to 1/2 times the sine of e to the x raised to the minus 1/2 times this derivative. Right, so this is the sine of a function of x. But chain rule, the sine of a function of x is equal to cosine, right? Derivative sine is cosine. And the argument going into the cosine function is this inner function, e to the x. So the derivative of sine of e to the x is cosine e to the x. And then we got to multiply that by the derivative of this inner function, e to the x. Man, this chalk up here is hard to deal with. It's like they never clean up the chalk up here. Well, we know what the derivative of e to the x with respect to x is, right? So the derivative of y with respect to x is equal to 1/2 times the sine of e to the x to the minus 1/2 times the cosine of e to the x times e to the x. That's the derivative of this function right here, y equals this. Right? Good stuff, isn't it? Yeah. All right. Why is it called the chain rule? Because in finding this derivative, we work from the outside to the inside, right? First, we found the derivative using the general power rule, right? Sine of e to the x is on the inside, right? This is a function raised to the 1/2 power, right? So first we applied general power rule. And then we had to find the derivative of sine of e to the x. So we took the derivative of sine, it's the outer function. And then lastly, we took the derivative of e to the x, okay? So whenever you have, with the chain rule, right, you have a composite function, right, a function inside a function, inside a function, inside a function. You start with the outer function and you work inward, right? So just to push that point. So if I have y equals I don't know if I can come up with another example, right? So I have y equals the tangent of the secant of the sine of x. So we got 1, 2. So we take sine of x is going into the secant function, and secant sine of x is going into the tangent function. So to differentiate this, I don't know if I want to write this all out. We start from the outside in. First we take the derivative of the tangent function. And the derivative of the tangent function is secant squared, right? So we have secant squared of the secant of sine x, right? So this is the argument going into the tangent function. So that's the inner function going into the tangent function. Derivative tangent is secant squared. So we have secant squared of secant sine x. And now we multiply this by the derivative of secant of sine x. What's the derivative of secant? Secant tangent, right? So we have secant of sine x times tangent of sine x times the derivative of the inner function sine x. What's the derivative of sine x? Cosine x. See, over here, I broke it down in finding this derivative. I did 1, 2, 3 passes to get the derivative. Once you understand with the chain rule, you start from the outside and work in. You won't have to do, with a lot of practice, you won't have to do 3 passes. You'll be able to write out the derivative within 1 pass. As long as you understand, you're starting from the outside working in. So derivative tangent is secant squared, and the argument is secant sine. So derivative tangent is secant squared of secant of sine x. And now you got to multiply this by the derivative of secant sine of x. Well, the derivative of secant is secant times tangent, and the input is sine x. And then lastly, you got to multiply that by the derivative of sine x, which is cosine x. Okay? It's the pattern, right? Once you know the pattern, right? You know the rules of differentiation. You know the pattern. I mean, it really isn't that bad. Okay. All right. So let's find the equation of a tangent line, where we gotta use the chain rule. So let's find the equation of the tangent line to the curve y is equal to the sine of the sine of x. So you know the domain of the sine function is all real numbers, and the range is -1 to 1. So the sine of x is a number between -1 and 1, and then you're taking the sine of that number between -1 and 1. Okay? So this is a continuous function. Okay? All right. And we're going to find the point of the equation of the tangent line at the point pi 0. Remember, pi is the x coordinate, 0 is the y coordinate. Okay? And that point indeed is on the graph of this function, this function, because when I put in pi in for x, right, I have the sine of the sine of pi, and you should know that the sine of pi is 0, so we have the sine of 0, which is 0. So when x is equal to pi, y is equal to 0. Okay. All right. So to find the equation of the tangent line to the curve, you know that the slope of the tangent line and the slope of the curve are the same at this point in tangency, right? Pi 0. So we need the derivative of y in order to know what the slope of the tangent curve is. Or tangent line, excuse me. So the derivative of y with respect to x, remember you start from the outside and work in, right? So derivative sine is cosine. So we have the cosine of the sine of x, right? Remember, this sine of x here in parentheses is the inner function, okay? And this sine is the outer function. So when we differentiate the outer function sine, we get cosine, and we evaluate the cosine at sine of x. That's what this is. And then we got to multiply this by the derivative of the inner function sine x. So the derivative of y with respect to x is equal to the cosine of the sine of x times the derivative of sine of x with respect to x, which is cosine x. Now to find the slope of the curve and the tangent line at the point pi 0, we evaluate the derivative at x equals pi. When using Leibniz notation, right, and we're evaluating the derivative at a specific value of x, right, we put a bar behind dy over dx and specify what the value of x is. And so when we put in pi in for x on the right-hand side, we have the cosine of the sine of pi times the cosine of pi. Well, the sine of pi is 0, so we have the cosine of 0 times the cosine of pi, which is -1. And the cosine of 0, you know, is equal to 1. So we have 1 times -1, which is -1. So the slope of the tangent line, the slope of the curve, right, are the same at x equals pi. So m equal to -1, right, is the slope of the tangent line. We write the equation of the tangent line in y equals mx plus b form, right? Slope-intercept form. M is equal to -1. So you can write y is equal to -1 times x plus b, right? Or negative x plus b. And then to find the y-intercept b, we use the point pi 0. Right? Because both the tangent line and the curve go through that point. So we put 0 in for y, pi in for x, and we solve for b. Well, -1 times pi is pi. -1 times pi is minus pi. So we add pi to both sides, you get b is equal to pi. So putting in pi in for b right here, we have y is equal to -x plus pi. That's the equation of the tangent line. Any questions on that? So you have everything you need to successfully complete the web assigned homework due Monday night. Okay? This 3.4 will not be on the quiz, but it'll be on the exam. Okay? So I have the lecture handout for 3.5. So I want to give that to you now.